Okay, so welcome again to the course Fundamentals of Solar Photovoltaics and Technologies. Today again a new lecture. We will continue our discussion about materials for solar photovoltaics, looking at the semiconductors. So let's just briefly recap what we did in the last class. So in the last class we looked at electronic conductivity in metals, which is represented as sigma, and it's Ne square tau divided by m. And we saw that electronic conductivity is highest for metals, going of the order of 10 to the power 4, 10 to the power 6 ohm centimeter inverse. Semiconductor, on the other hand, we have insulators which have conductivities smaller than 10 to the power minus 10, 10 to the power minus 12 ohm centimeter inverse, in fact even lower, and somewhere in between around 10 to the power 0 to 10 to the power minus 2 to, let's say, plus 2 or 10 to the power 0, we have semiconductors. It's not a very fixed range, but broadly around that range. Different semiconductors will have different conductivities and also at different temperatures. The classical model of electronic conduction, in which we consider electron as a particle, does not explain the observed behavior of semiconductors, even the behavior of metals, such as their specific heat calculations versus measurements and temperature dependence of conductivity of semiconductors, the presence of holes in materials, especially in semiconductors. So these things are not explained by classical model, and that is why there is a need to consider the dual nature of electron, which is wave and particle kind of nature. So this was first proposed by de Broglie, who said that electron can act as both particle and wave, and if that is the case, then we can correlate the momentum of electron, which is particle like nature, is equal to h cross k. So here p is momentum, which can be written as mv, and k is wave vector, whose magnitude is 2 pi divided by lambda. So wave vector is also a vectorial quantity, and you can notice that the units of wave vector is inverse of length. So as a result, it's a reciprocal to length. Quantity with the units being meter inverse. So this was the first hypothesis that related the particle like property, that is momentum, with the wavelength of a wave, that is electron in this case, and this went a long way in proving in explaining the behavior of semiconductors and even metals. Electron as a wave must have wave like properties such as wave velocity, wavelength, frequency, and wave numbers or wave vector, and this is characterized by a function called as wave function, which can totally explain the electron's behavior, and the analysis of this wave function allows you to do certain calculations which can help one explain the electronic conduction in materials. So to begin with, we start with what we call as free electron approximation, that electron is free. It considers dual nature of electron, that is de Broglie's hypothesis. Electron energy is followed as E, which is kinetic energy, which is h cross square k square divided by 2m, and this follows from the relation P is equal to mv. So we know that E is equal to half mv square, and if we replace the value of V, we will get the kinetic energy of electron as h cross square k square divided by 2m, where k is the wave number and or wave vector, and m is the mass of the electron. And this is then plugged into what we call as Schrodinger's equation. So Schrodinger equation is a equation which was given by Erwin Schrodinger, which connects the potential energy of electron as well as kinetic energy of electron and makes it equal to the total energy of electron in both time dependent and time independent spaces. For the sake of for the sake of understanding of band structure or band theory of materials, time independent part is what we solve with appropriate boundary conditions. So, it is this part on the left that we will consider for rest of the analysis, which is minus h cross square 2m del square psi plus v psi, and psi is the wave function here. So, this is the wave function and this is called as Hamiltonian, which is a mathematical operator. So, without getting into too much of Hamiltonian mechanics, this equation is solved, the time dependent part is solved by applying appropriate boundary conditions, as we will see in next few slides. So, the first in this theory, free electron theory as we call it, we use this time independent part, which is sum of kinetic and potential energy, which is equal to total energy. So, we write this as minus h cross square divided by 2m into del 2 psi, which is the kinetic part, and del 2 psi is the Hamiltonian operator, plus v psi, and this v psi is the potential energy. This is equal to the total energy of electron. We assume that electron is free and it does not have any interaction, there is no interaction between the two electrons and there is no interaction between electrons and ions. The free electron is confined within a cube of side L, whose volume can be written as L cube, and we apply boundary conditions that the wave function at the boundaries is same. So, if you have a cube like this, so this is let us say 0 and this is L. So, wave function here and wave function here is same. So, psi at x plus L y z is equal to psi at x y z, psi at x y plus L z is equal to psi x y z, and psi x plus x y and z plus L is equal to psi x y z. And if you take a general solution, the general solution of this will be of the form psi r, which is a position dependent wave function, is equal to 1 over root v into exponential of I k dot r, where I k dot r basically is the phase factor. So, you can see that this is dot product of wave vector with the position vector. We will solve this equation in the context of certain specific cases, as we will see in the next few slides. So, we are not going to details of quantum mechanics. Detailed quantum mechanics you can see from, you can read the electronic properties of materials by R.E. Hummel, and there is also a very nice book which is physics of solid state, or I think the solid state by Guinea and Julian. This is again a very nice book to read about the electronic behavior of materials, and or you can go to electronic properties of materials by R.E. Hummel. Another text that you can look at is solid state physics by Charles Kittel. So, this book and this book, these are easily accessible and available books, and for learning details of quantum treatment of electron theory, you can go through these books. So, let us just first consider electron in a free space, that is, there is no potential applied at all. So, electron is in a free space without any external potential. We can modify this equation, the previous equation, then as, since V is equal to 0, the second term in the equation becomes 0. So, then we can write this equation as h cross square 2m into del 2 psi by del x2 plus E y is equal to 0. And the solution for this, it is a second order equation. The solution for general solution for this will be equal to a exponential of I k x, where k is given as 2 square root of 2 m e divided by h cross square, because we know that E is equal to h cross square k square divided by 2m. So, this gives us E is equal to h cross square k square divided by 2m, and what it shows you that electron can take any state depending upon the k value. So, electron is free, there is electron, there is an energy continuum. So, if you plot this, it is a parabola like this, and electron can take any state. So, it resides basically in a free space without any potential, and it can reside anywhere it wants. But this is not what we observe for materials. So, we need to look at another case, which is electron or particle in an infinite potential well. So, here what we consider is that electron is in a potential well. So, this is a well of, let us say, length L or width L. At the boundary of the well, the potential is infinity, and within the well, the potential is equal to 0. So, basically what it means is that electron can be within the well, but it cannot move out of the well, because the potential outside at the walls is infinity, and hence it cannot jump over the well. So, basically in this region 1, so basically wave function will exist only within region 1, it will terminate at the boundaries of region 1 and 2 and region 1 and 3. So, wave function will not exist between region 2 and 3. So, in region 1 we can write wave function again as minus h cross square by 2m into del 2 psi by del x2 is equal to E psi, and k we know what it is, it is square root of 2 me by h cross square. We can write psi 1 as, so this is in region 1, so psi 1 will be, write this as psi 1 maybe. So, we can write psi 1 x as a to the power e I k x plus b e to the power minus I k x, which can be simplified as a cos k x plus b sin cos k x. We know that in the region 2 and 3, because of infinite potential barrier at the walls of the well, psi has to be 0 within these two regions, and as a result we can take psi 2 and psi 3 to be equal to 0. If that is the case, then psi 1 x we know it is a cos k x plus b sin k x, and but we also have to ensure that psi is continuous, which means psi at 0 is equal to 0, which will give us a is equal to 0, psi at L is equal to 0, which will give us b sin k L to be equal to 0, which means sin k L is equal to 0, and if sin k L is equal to 0, in that case we can write k L should be equal to n pi, where n is an integer, either 1, 2, 3 and so on and so forth. If you now replace the value of k in this expression, we will get the values of E, which is h cross square by 2m into n square pi square divided by L square. So, what we get is basically energy as a function of n, which is some number, some constant, multiplied by h cross square pi square divided by 2ml square. So, the two things which vary here, one is L, second is the n, and we can then put in the value, so psi 1 x can be written as then b sin n pi by Lx, and since we know that conjugate of psi and psi, the product of that over the entire length must be equal to 1, because particle must exist within that well. So, the product of these two integrated over the width of the well must be equal to 1. It has to be found somewhere, and total probability should be equal to 1. So, b can be then found as square root of 2L, and so psi 1 x will be square root of 2L into sine of n pi divided by L into x. So, if you plot now these values, so this is basically, you can see E n I can write as n square pi square into h cross square divided by 2ml square. So, if I take C as a constant, which is h cross square pi square divided by 2ml square, then basically it means that it is C into n square. So, essentially you can see that energy, so there is no zero energy, there is no electron at the bottom of the well. The first state is E1 is equal to 1C, which is at n is equal to 1, second is at n is equal to 2, 3, 4, 5, and they are varying as a function of n square, they are increasing. So, you can see the distance between these keeps increasing as a function of n square. Okay. So, basically these energies are quantized, there is no continuous energy state, The energy states are now quantized. There is no energy continuum. So, what it means is that if you have electron in an infinite potential well of width A or L, in this case L we have taken, then energy can be written as h cross squared k square divided by 2m, which is, in this case it will be A because we have taken the width as A. So, basically it varies in this fashion where it increases from n is equal to 1 to 2 to 3 to 4 to 5 in a quantized manner. So, there are no energy states between n is equal to 4 to 5, there is no energy state between n is equal to 3 to 4. An electron can only occupy the states which are discrete states, there is no continuum here. And so, you can plot the wave function and the properties, and wave function, whatever the nature of wave function, this is like a vibrating string, right. So, for n is equal to 1, this is the energy, this is the psi, nature of psi, this is for n is equal to 2, this is the nature of psi, for n is equal to 3, this is the nature of psi, but you can see that at the boundaries of well it always terminates. There is no electron to be found outside the well, and the difference between the two energy levels, successive energy levels, is proportional to 1 over L square, as you can see from this plot. And as the value of L decreases, the energy levels become closer and closer, and as the value of L increases, the energy levels become so for larger L, you can say for delta E decreases, and for a smaller L delta E will increase, and this has a profound influence in terms of electron confinement in molecules. So, molecules which show stronger confinement where L is smaller, the energy levels are closer to each other, but molecules which do not have so much of confinement, the L value is larger. So, L value is larger, in that case energy levels are much more closer to each other. So, the spread of energy levels will depend upon the extent of confinement of electrons within the molecule, and this is very true in case of things like benzene and pentacene. You take the single molecule, you take the 5 molecule state. So, when you take the single molecule, the energy levels are far more distant from each other, but when you take the 5 molecule state, the energy levels are far more closer to each other because the L is larger in that case. So, what we have considered here is a one dimensional case. So, how do we define n? We can define n as a quantum number. So, this is only 1 degree of freedom, plus it will give you spin state. So, every state can have a plus and minus, so up or down kind of configuration. So, each state can have 2 electrons residing at it, but when you go to 2D case, in the 2D case this whole thing becomes E is equal to h cross square pi square divided by 2m, and this n square is replaced by nx square plus ny square. So, you can see now you have 2 quantum numbers nx and ny, and which means you have 2 degrees of confinement including the spin states, which means you can recite 4 electrons. So, you have more degeneracy in the system. So, these are called as degenerate states. If you go to 3D, you will have 3 quantum numbers in a similar fashion plus a spin, and this is again similar to atomic model that we make with the different quantum states like n quantum state, L quantum state, m quantum state, and with S being the spin quantum number. The difference in 2D and 3D could be the way we look at it. So, in 2D we have to look at it in a Cartesian manner, but in 3D we can define the whole thing in a spherical symmetry also. But nevertheless, basically when you move from 1D to 3D, the degeneracy increases with the increase in the number of quantum states. So, basically what it tells you is that in an infinite potential well, the electron is confined within the potential well, and it occupies the energy states in a quantized manner. There is no continuous energy state, unlike we saw in case of a absolutely free electron when there was no potential anywhere at all. In the real cases, there might be a finite potential well, which means that the potential around the well is not infinity, but it is greater than 0. So, what you would expect from a particle in such a situation, that as long as the potential is higher than the energy of electron will not be able to jump. That is what the classical model says, but the wave like model gives us a different answer. It gives us an answer that electron has finite probability to exist outside the well the moment we consider it as a wave-like. So again we write the wave equation or the Schrodinger equation, which is minus h cross square by 2m del 2 psi by del x2 plus Vx psi is equal to E psi. Now V is not equal to 0 or infinity, it is now finite. For the first reason the wave function remains the same, that is A is equal to cos kx plus B sin kx, but for the other two regions, second region and third region, we have an exponentially decaying wave function, that is D is equal to D exponential minus alpha x and C exponential alpha x. And alpha and its derivative, the psi and d psi by dx should also be continuous across the boundary. So as you move from 1 to 2 or 1 to 3, the psi should not be discontinuous, it should be continuous, as well as its derivative should also be. So psi and d psi by dx must both be continuous, and when you apply appropriate boundary conditions and take the derivatives and solve them, so we find the value of alpha as k tan KL divided by 2, and if we plot these wave functions now, we see that wave function does travel outside the box. So it is no longer 0 here, we see that it is a finite probability. So basically if you have psi value finite outside the well, which means the probability psi star must also be finite. So what it tells us is that electron has finite probability to be found outside the well. So wave function decays exponentially outside the well. There is a finite probability that electron will be found outside the well. Now this is a very startling result, because if you have electron as a particle, the particle cannot jump this barrier because this barrier is higher than the energy of the particle. But if you consider the wave-like nature of electron, it shows that there is a finite probability of electron moving outside the well, and this is the phenomena that we use in principles like tunneling. So when you have very thin oxide layers between, let us say, two metals, that is how the electron tunnels through the thin oxide layer, even though oxide layer is far more insulating than the metal. So basically what you can say is that, now here we are considering only for a very limited case, but let us say you have a material which has 1 mole of atoms. 1 mole of atoms will give you large number of electrons. So if you go from one atom to multi-atom system, one atom will show you one state, two electrons will show you two states, three atoms will show you three states, 4 atoms will give you 4 states, and likewise these states keep on developing, and the moment you reach this 1 mole of material, which means you have 6.023 into 10 to the power 23 atoms, you will have so many energy levels, and all of them are sandwiched between, let us say the width of the band is 6 electron volt, or so within a band of 6 electron volt you will have all of these bands against each other. So if you just divide the 6, let us say the width is 6 electron volt, and if you divide 6 eV by 10 to the power 23, 6 into 10 to the power 23 atoms, then we see that the gap between two levels is approximately 10 to the power minus 23 eV, which is very, very tiny. 10 to the power minus 23 is extremely small energy gap, which means this energy state is like a quasi-continuum. Although these energy states are discrete states, but for a given material, the distance between these energy levels is extremely small, so these are very, very closely spaced energy levels, and that is why this is called as a quasi-continuum of energy landscape. So basically what happens is that when you have a free electron, when it is not bound, electron can occupy any state, which is shown by B. So this gives me basically h cross square k square divided by 2m, and it can occupy any energy. This is for bound electrons, which means electrons reside in a large potential, such as in the vicinity of an ion, where there is a large potential for electron to go anywhere else. So if that is the case, then we have a scenario n square pi square h cross square divided by 2ml square. Then we have quantized energy state. But what happens for an electron within a finite potential that is in a solid? what we encounter is these bands. So, we have thin bands at the bottom, and these bands become broader and broader as you go to higher energy states. And this is, so if you keep the atoms if you bring the atoms very close to each other, the bands start overlapping. If you keep the atoms very far from each other, so this is the case of isolated atoms, right? This is the case of electron being in this is the case of electron in a continuum. Energy states are continuous, right? There is a electron can move anywhere. And this is what we get for materials typically. We have this energy level followed by a gap, followed by this energy band, followed by a gap, then again a band. So, what is the reason? Why do we get this kind of picture for a given solid? Looking at for a material, typical material, especially for materials like semiconductors, etc. This is the band structure that emerges, and we need to explain why does this happen. So, what we did in this lecture, we'll briefly looked at electron as a wave. So, we established a wave function. This was solved using Schrodinger's equation, looking at the potential and kinetic energy. We solved two cases. First case in which electron was free, it has no potential energy whatsoever. So, it could occupy any energy state it wanted, which means it was in an energy continuum. But second case that we looked at was an electron being in a potential, either infinite potential or a finite potential. In case of infinite potential, it shows the solution shows quantization of energy states, which means electron cannot occupy any energy, it can occupy only the designated energy levels in an increasing order of energy. And if the wave function, if the potential at the boundaries was not infinite but finite, then wave function can be found outside the well, suggesting that wave electron has a finite probability of being found outside. But in reality, in materials, what we see is formation of energy bands which are separated by a gap, and we now need to see why does this happen. So, we will stop here and we will cover this aspect in the next class. Thank you.